are very useful and they are very neat looking. It's basically cyclohexane, cycloalkane replace one of the carbon with oxygen. I'll give you this. The epoxide, as you can see, it is the 3 carbon. It's related to the cyclopropane with one of the methylene group C2 replaced by oxygen. And the name in the IUPAC name is oxyranes. Oxyrane. Also, we call it epoxide. This only applies to the 3 carbon, 3 atom ring with oxygen in it. And so the other ethers, they are more behave like regular ethers, chemically very stable and need a strong acid and for a long time to break it down into alkyl halides. That's pretty much the only reaction they will involve to. The 3 carbon, because high stress, very high stress in the ring structure, it is much more reactive. And so the reactions, we call them epoxide, and they are more reactive because of stress in the ring. The epoxide structure in nature, we can see there's some pheromones have epoxide. So this kind of epoxide in the biomolecules is very likely to combine and react. So could be the reason why they are as hormones, because those molecules may interact with a receptor in the body, and such a reaction can cause a cascade of all different kind of reactions. And this molecule, you can see this is the also pheromone, have 2 epoxide structures. By the way, the identify the epoxide structure from nature, the natural product, is very challenging because epoxide is very reactive. So if the process not been careful enough, we can easily destroy those rings and misidentify the compound from nature. The epoxide in our everyday life has a big use. It is in the forming the resins. It basically form very strong structure. It is very special glue, and this kind of glue is a 2-part glue. By the way, you can buy it from the store. They call it epoxy glue. And the epoxy glue, it is based on the epoxide. Okay, this part comes from the epoxide. It was epoxide like this. And this is the other component. It's basically diamine. So basically, the epoxy glue in the industry, in the everyday life we use, it is of 2 parts. One part that has diamine, the other part have the epoxide, and when these 2 reaction is a nucleophilic reaction, a nucleophilic substitution reaction. It'll open up a ring, and all the structures start linked together, very strong. BPA also use epoxide from the ring. This part is the epoxide, and the other is chloride. The epoxide naming, there's 2 ways to name the epoxide. We either name as this oxygen as a group, okay, treat it as a group. We just need to locate which carbon has this group. And it'll be similar as we name the other compound. We'll find the longest chain and give a substituent as low number as possible, or as many substituent as a small number as possible, and so forth. And so basically this compound, we find it as if we name it as alkane and use epoxy group, then we find the longest chain with as a parent. And then the position 2 has part of the epoxide group, position 2. Position 2 also has a methyl group, and position 3 has the ethyl group and the other part of the epoxy group. So the naming, you can see the namings. Epoxy pentane is together the parent. We just need to show the location for the epoxy group, and of course show those substituents first. Okay, so the first naming group is we name is epoxy alkane, and name is epoxy alkane, and then we name the substituent. Position 2 has a methyl, position 3 have ethyl, so 3 ethyl first, 2 methyl, and then this is the parent and the location for the epoxy bond. So the naming is similar to the alkene naming. If you remember the alkene naming, alkene naming is in the end has as this. Position 2 shows where the double bond is. Here the epoxy bond, we show the 2 and 3 because epoxy, the oxygen need to have a form 2 bond with the parent chain. So this is the first naming use. We use epoxy ane, epoxy alkane naming. The other way is the oxyrane. We name is oxyrane. The oxyrane means this is the parent. Okay, this is the parent. And then this parent, and that means we have on this side we have 2 ethyl group. This side have 2 methyl group. And since either way, those 2 carbons in the oxyrane have 2 substituents, so that makes them equal. So that means next we'll boil down to the alphabetic order. Position 2, you got a 2 ethyl group. The position 2 can be either this 2 or the other way around. Okay, this is the other way around. The difference is by naming the use my red underlined number, you get the 2,2 dimethyl, 3,3 diethyl. If you follow the blue letter numbering, you get a 2,2 diethyl, 3,3 dimethyl. It seems like the same. The difference is ethyl has high priority than methyl. So therefore we give the ethyl the number is 2 and the methyl is number 3. So basically the same naming system we go over again. So there are 2 ways. There are 2 ways to name the epoxy group, either epoxy ane or oxyrane. The first compound, the parent, it will be, this will be the parent. And so either this is number 1 or this is number 1. We need to go through the epoxide structure. So if this is number 1, we go clockwise. If this one is number 1, it'll be counterclockwise. And obviously the counterclockwise reach the substituent, the ethoxy group, sooner. So we should go with the counterclockwise, use this number 1. If you use this number 1 and clockwise runs through the epoxide bond, that would be number 6 as the ethoxide. So that's not good. It's better with the counterclockwise, and this is number 1. And so number 1, this is the parent will be the cyclohexane. and the epoxy bond is on the between 1 and 2. Epoxy, we should have XY. Epoxy, cyclohexane. Okay, this is the parent name. And the carbons 1, 2. With a ring, by the way, with ring, the 1 and 2 is not necessary. With the straight open chain, yes, you need to show where the number 1, number 2 carbon is, whatever a carbon is. But for the ring, it's not necessary to show the 1 and 2. And then we have the 1, 2. Position 3 have alkoxy, so that'll be 3. 3 has 3 azoxyl. It is basically named like ether. Okay, 3 azoxyl epoxy cyclohexane. So that's the parent. There are 3 chiral centers in the molecule, by the way. This carbon, now it is chiral center, and so is the epoxy group. And so we need to worry about the RNS. So position 1, the RS, position 1, if I draw separate. Okay, so this carbon, the number 1 carbon, you have a 1 hydrogen as a dash, and so oxygen highest priority, this carbon second priority, and this number 3. So this be the S. The number 1 is S. And number 2 oxygen highest priority, and then this will be higher priority than this. So this will be the R. This carbon is R. And finally, this carbon, the oxy group has high priority, and this is second priority. So if the alkoxy bond is a wedge, that should be R. But since it actually is dash, so this is S. So the name for the compound will be 1S, 2R, 3S, all in parentheses, and hyphen, and then 3 azoxy epoxy cyclohexane. It's a very long, messy name. By the way, this compound, we cannot name it as oxyrain, because oxyrain, we based on the epoxide structure. This would be the oxyrain. And we need to have a fourth substituent or separated, not linked together. If these two link together, that would not be possible to name. And so we don't name this, use the oxyrain way. But for this one, yes, this one we can use both ways. This both ways, and so this will be the oxyrain. We have both ways. We can either find the parent and name that. The parent will be the epoxy hexane. This will be the parent. And there are 6 carbons, so it is the epoxy hexane. And obviously, the epoxy bond right in the middle of the 6 carbon structure. It's almost symmetrical. So that means this has to be number 1, which will give you the azoxy group as a small number as possible. This one is better. It's not good for number 1 because the azoxide will be too late, too high number. So anyway, we have this one number 1, 2 have an azoxy group, and so we have a naming will be the parent. The parent will be 1, 2, 3. 3 and 4 epoxy hexane. This is parent, and position 2 has a sulfide group. So that'd be the naming without stereochemistry. And of course, we can add stereochemistry later. Okay, you can always add that later by yourself. I'm going to move on to the next way. The other way to name this as oxyrain. The parent will be oxyrain. Oxyrain means it is almost like cyclohexane with one carbon replaced by oxygen. That's what we call oxyrain. All right, so the oxyrain, we're looking at this structure. Focus on this part. And with oxyrain, we have this is a big alkyl group. This is a very small, just acid group. So it's a very easy name the acid group. But with this big chunk as the alkyl group, that'd be a very hard name. You will name this as the ethyl group, and position 1 has a ethoxy group. So the naming will be 1 ethoxy ethyl, all in parentheses, and the alkyl group. That's too much. As oxyrain is too much a challenge to name this part. So I'm going to give up. I'm going to stay with the epoxy hexane, just because of the complexity of the alkyl group in the structure. Okay, I think today we are done with the lecture. We'll just use up all the time. The synthesis of epoxide, this is mainly from the alkene compound. Because in the alkene with peroxy acids, such as MCPPA. MCPPA is it is basically a peroxy acid of a benzoic acid. Okay, this would be the benzoic acid with a benzene ring only, and this is one of the derivatives of the benzoic acid. And you have the peroxide bond here. This can be used to add a single oxygen atom on the alkene double bond, so form the epoxide. And so it can be also the peroxy acetic acid. So basically acetic acid replace OH, replace oxygen with the peroxide bond. Can be also used for forming the epoxide. And so the because oxygens add on the one side of the double bond, you can see the retention of the substituent. Whichever substituent on the same side of the double bond, they will stay on the same side. And so that's, of course, there's a, we added the RS stereochemistry on the center. And also we can use halohydrin. The halohydrin is basically a beta chlorinated alcohol. Okay, beta chlorinated alcohol. So this is alcohol. This is alpha carbon. Beta has a halogen. So it can form. The epoxide can form from this compound. This compound, halohydrin, it is coming from the halogen and the water together, add on the alkene functional group. And the halogen water adding to the alkene reaction started with the a positive charge, a cation on the carbon-carbon double bond, and followed by the solvent attack, nucleophilic attack by the solvent. So this is kind of how the halohydrin is formed from the alkene. At first, with the halogen, which is electrophilic, it formed the halogen cation. and then this followed by the water nucleophilic water attack, and this bond break to give us some halohydrin as a final product. The halohydrin formation reaction is Markovnikov, which means the OH group, which comes from nucleophile, is attacked on the carbon with more substituent. And the reaction is anti-stereochemistry because SN2 reaction. Okay, so this is how the halohydrin is made. And the halohydrin, now it can be treated with sodium hydroxide, and it can form the ring. So basically, this is the with a strong base, it will make this oxygen more nucleophilic and attack on the bromine and form the ring. So this is the other way to form the epoxide. Start from the halohydrin. And the reaction mechanism, it is the started with the protonation. As you remember, the neutral hydroxy group, it is basically this entire thing is alcohol. Alcohol, which it is nucleophile, but it's not a very strong nucleophile. But after the partially deprotonated by the hydroxy group, okay, the hydroxy group, the hydroxide ion in the solution from the sodium hydroxide, it can take away the proton, turn the oxygen to negative charge. And once the oxygen becomes negative charge, the entire thing becomes a alkoxide ion, which is a much stronger nucleophile. Then this nucleophile, it will attack within the molecules. This reaction is intramolecular. Okay, it happens inside the molecule, within the molecule. The intramolecular SN2 reaction, the lone pair electrons attack on the backside of the carbon, and the carbon bromine bond dissociate. So this attack from the backside. Okay, the oxygen is close to us because of which, and the oxide close to us attacks the carbon, and so that the bromine that is away from us will leave. And so that's the stereochemistry, looks like that. If you draw the ring structure, the cyclohexane, the chair conformation, it looks better. So here's the hydrogen, and the oxygen attack from top and kick away the bromide. This is typical SN2 reaction. The inversion occurs. The nucleophile attack from behind the leaving group. So this is one way to, this is the other way to form the epoxide compound. And so we have two ways. And that's to summarize these two together. When we have a alkene, it can be either use MCPBA, add oxygen on the double bond, or form the halohydrin. So here's the bromohydrin. Okay, we use a bromine in water, and bromine and water together. It is essentially we add this piece as if we add this piece to the alkene. And of course, bromine will add first because bromine is electrophilic, and the double bond is abundance of electrons. So that's the first step. We add to become a halohydrin, and then the sixth step, the base catalyze the intramolecular SN2 reaction to form the epoxide. So the stereochemistry for this reaction, because stereochemistry is when you have an alkene that is asymmetrical. Okay, if you have alkenes asymmetrical, then we have a pair of enantiomers. So for example, this compound, this will be the trans, or we call this as a E, the E isomer, And this reaction react with the MCPBA, then the reaction product, we have a pair of enantiomers. So once I add the MCPBA, the molecule becomes three-dimensional. So I have to adjust accordingly. So this is one of the products. Me for methyl, ET for ethyl. And so we have this. This is one of the products. The other product is a mirror image. So basically, the oxygen will be downward. The oxygen will be downward. Or you switch these two, both. You get the other product. Now the isopropyl on the other side, and a wedge on the methyl group. Okay. And the dash is the methyl group, and the wedge is the ethyl group. So complete reverse, complete mirror image. That'll give me the other product. You have a pair of these because the attack come from both sides of the molecule, and that's equal opportunity. In the end, you have a one-to-one ratio between these two enantiomers. So that'll give you a racemic product. The other way reaction is in halohydrin or bromohydrin, and the first step give you the form the alcohol like this. Oh, by the way, this reaction, when you form the halohydrin, you got a whole bunch of a mixture of halohydrin. Very complicated. Okay, so let's just use a line here. And by the way, between these two carbon, both carbon attached with 3 carbons. So between these two carbon, there's no difference in terms of Markovnikov or anti-Markovnikov. The same. These two carbon essentially the same. They are both the tertiary carbon once we add some functional group. So the product we get is we got both this and that. And regardless of chiral center. So basically we got 2 pairs of enantiomers. But nevertheless, once we add the sodium hydroxide, form the epoxide, this attack that form bond, give you epoxide. This attack that form epoxide, you're gonna still the same, only 1 pair of enantiomers. So because we add some kind of asymmetry in the structure. So anyway, that's the intermediate. We got 2 pairs of enantiomers as the halohydrin. But once we add the base to cause the intramolecular substitution reaction, SN2 reaction, we get only 1 pair of epoxide enantiomers. Okay, so the epoxide can be prepared in these 2 ways. The reactions of top epoxide, the epoxide are much more reactive than the ether. Okay, that's to begin with. We need to make this very clear. It's much more reactive. The ether can be, they are so stable, can be used for solvent. The epoxide, not so. They are so reactive. They are used in many chemical reactions, such as using as a glue, the epoxy glue. And they are more reactive. So the reactions, of course, because the significant ring strain, the bond angle in the epoxide is only about 6 degrees. And supposedly the sp3 hybridization carbon should have only about 109.5 degrees. So that's a big stress in the structure, making them more reactive, high energy. And if we use that for synthesis, they're great for synthesis because they're more reactive. And so the ring opening can be started with alkaline conditions. Okay, this is in the alkaline conditions. Strong nucleophiles. Okay, do you remember the strong nucleophiles are the sulfur compound, the best. Iodide, bromide, cyanide, and alkoxide, hydroxide. These are all great nucleophiles. The nucleophiles, because this carbon is high stress, making the energy high, and also carbon here linked with oxygen, make it more positive, so make it more attract to the negative charge come from the nucleophiles. So this attack happens and ring opened, and once you form this, you realize this is basically the deprotonated thiol. And so if the reaction condition have some protic solvent, such as water, the protic solvent can give protons to the alkoxide and finally give us a thiol. And so that's the first reaction. Well, this reaction actually is not very useful because it's just making alcohol. Alcohol is not a big deal. It's very common. But we gotta just briefly go over the stereochemistry, where this epoxide ring open will take place. When the epoxide is symmetrical, like we saw in the last slide, you get only one product. It doesn't matter nucleophile attack from this carbon or that carbon, give you one product. But when you have the attack by a strong base nucleophile and on the asymmetrical epoxide, the steric effect is basically when we attack by the this is nucleophile attack, and the reaction is SN2. And if you remember, SN2 reaction is very sensitive to the steric effect, which means the substrate. How is the carbon with the leaving group blocked or more avoidable? Primary carbon, the primary alkyl halide is most readily goes through the SN2 reaction. Tertiary will not go through SN2 because too many alkyl groups substituent around, blocking the excess. So same as here, because this is SN2 reaction, and SN2 reaction is sensitive to the steric effect, the bulky alkyl groups on the substrate. And we have, this is basically a substrate. This is nucleophile. The substrate with the leaving group. Leaving group is the oxygen, kind of oxygen with carbon. And it can be either attack here or attack here. And obviously, attack from this direction, we have three alkyl groups. This is the tertiary carbon. And where this one have one hydrogen, so less blocked, more available for a reaction. So therefore, the reaction takes place on this carbon as a major product. And the attack with the oxygen as dash, that means oxygen is away from me. And so if you have the nucleophilic attack reaction taking place, this is how the arrow pushing will go. Start from the long pair, and I need to delete this. All right, so attack on here, because this is secondary carbon, and this bond break, electron go back to oxygen. And so after this, we get the product. Okay. We're attacking on this carbon from my side, okay, so that the oxygen away from me can break from this carbon. So therefore, the nucleophile added carbon bond is a wedge. And the hydrogen now become dash. We don't need to show the hydrogen. Okay. And on this carbon, there's no new bond formed. It is basically just the oxygen. The oxygen becomes negative charge and the methyl group is here. So that's the immediate product. And this reaction has to be in some kind of the protein solvent, such as methanol. So the methanol will give the protons to this alkoxide to turn that into the diol. And this is proton transfer reaction. There we go. And this bond breaks and finally give us diol. Oh, should be dash. And the methoxide coming from the nucleophile is here. So we have only one product. This should be the major product. Okay, this should be the major product. So by the nucleophiles, and we have learned so many nucleophiles. We have alkoxide nucleophile, cyanide as nucleophile, because the carbon have very strong affinity to a electrophilic carbon. This is a sulfur, nucleophile. This is going to be interesting. This is a Grignard reagents. And the Grignard reagents we learn in the alcohol chapter. Very important to build a new, adding more carbons to the structure. If there's a carbonyl group, you just turn whatever you want to add in, turn that to the Grignard reagents. And the reactor is carbonyl. Will give us the alcohol at the same time adding carbons. So this is actually very, very important. And you can see the important is the alkyl. This alkyl group, because bonded with magnesium, it has a negative charge. So the alkyl or alkylide negative charge ion, carbon ion, it is in effect the nucleophile. First step will give you the ring open to give you alkoxide, and last step, the second step, by adding water, we protonate the alkoxide intermediate, reaction intermediates. Okay, the last one is not very useful. Okay, it is kind of bringing up what do we remember that we just learned in the alcohol chapter. Lithium aluminum hydride. This is a very strong reducing agent. And this reducing agent is basically the hydride as a nucleophile. By the way, hydride is a very poor nucleophile. But in this condition, when you have a epoxide, highly stressful structure, it will react with the hydride, even though hydride is a very poor nucleophile. And hydride attack on the carbon, it formed the carbon-hydrogen bond. The product, it becomes the alcohol. Okay, by the way, if someone works very hard to make epoxide, we don't want this epoxide becomes some kind of a alcohol without adding more carbons. So this reaction takes place. We need to know what is the reaction product, but it's not interesting, not useful in synthesis. Okay, not useful synthesis, because there are many other ways to turn the alkene into alcohol direct without going through epoxide. Okay, so if the reaction, so far those reactions are all SN2, which means the substrate, the steric effect on the substrate is very, very important. And that means if the two locations can be attacked by the nucleophile, these two locations, whichever has a less blocking by the alkyl group, will be the one that gives a major product. So, and you can see this is the first is asymmetrical epoxide. between this carbon and this carbon, they are different. They're linked with different substituent, different steric effect. So with this epoxide nucleophile attack between these two, this is basically a primary carbon with a leaving group. This is a tertiary carbon with a leaving group. So definitely nucleophile attack will attack on this. And then this bond breaks. So by doing that, first step, you will have a alkoxide ion. And the nucleophile form bond. And the second step with water. Water be able to give protons to the alkoxide and finally give us the alcohol. So that's our final product. The attack happens on the less blocked, the one with the fewer substituent. All right, so this second one is we're dealing with these one of the stereoisomers of this asymmetrical epoxide. Between these two carbons different. So this is asymmetrical epoxide. And so the reaction takes place, it should be on this carbon. Nucleophile should attack from this carbon. Okay, the oxygen is a wedge. Okay, so this bond will break and form the alkoxide. The nucleophiles attack from behind. So the final product, I'll just combine these two steps into one, just show you the final alcohol. The attacking nucleophile, it should be dash, because attacking from the other side. The oxygen is close to me, and the nucleophile attack from the other side. So that's why the formed bond is dash. And then we look at this carbon. This carbon, oxygen, this bond did not break. So that means whatever steric wedge dash, stay the same way. This oxygen should become the alcohol because of water, the protonation. And this methyl group, nothing happened. It's still the same methyl group. So when you have an asymmetrical, one of the stereoisomers of a epoxide, you get only one product is a major product. And so for this reaction, keep in mind the SN2 reaction. So there's basically a sort of inversion. Inversion happens on here. Inversion happens on this carbon. Okay, if the ring opening happens in the acidic solutions, it is different. Acidic, and typically the acid will be the hydrohallic acid. And this reaction is opposite of the halohydrin to mercury epoxide reaction. This is we just saw a moment ago. From the halohydrin, we add a base, and that will produce an epoxide. Now that's with base. Now with epoxide and with acid, the reaction can reverse. And so the reaction acid catalyzed reaction always started with the protonation. Protonation in the substitution reaction make a better leaving group, as always, because that protonation increases the positive charge, and the positive charge make it a better leaving group. So the first step, epoxide, the oxygen as the base, be protonated by the acid, give you the, this is basically a protonated epoxide. It almost looks like a protonated ether, okay? And with a protonated ether, then the this entire group, it becomes a better leaving group, just like a protonated alcohol. This becomes a better leaving group. And so the next step is the halide. that come from the acid have the nucleophilic attack on this carbon, break this bond. So finally give us the reaction is SN2, and it'll give us halohydrin as a product. By the way, this reaction is very similar to the cyclic ether that we saw last lecture. Okay, when you go through the reaction with the acid, the ring opens, and all the carbons still stay in the molecules. There are 4 carbons, so 1, 2, 3, 4, and the other side becomes the halogen. So that'd be the first step. This alcohol, if there's an excess of the acid, eventually will become dihalides. So that's a different story. With epoxide halohydrin, we just show that the rings opened. And if the reaction happens with acid and the reagent change, the ring open and the reaction solvent is the alcohol, we will get something different. Okay, the reaction becomes SN1 reactivity because the solvent is a protein solvent, and the oxygen become positive charge. It shows us the SN1 selectivity, which means the nucleophile attack on the carbon that is more substituted. Okay. Anyway, for this epoxide, it's symmetrical, so no difference. It doesn't matter SN1 or SN2. So the reaction product what we get is first step, proton add on the oxygen, and then the next step, water as a nucleophile to attack. Okay, so that's different from the last slide we just saw with the hydrohalide acid. Hydrohalide acid is the halide ion in the second step, in the second SN2 reaction. Here's the water as in the SN2 reaction. And so the reaction happens, the first step become protonated, and then the water attack this bond break, and you give us a diol. What you first get is not diol, it's actually the since water nucleophile, you get this first, and then deprotonated by the water. Finally give us diol. So that's with water as a solvent. If with alcohol and acid, the nucleophile is the alkoxide, and it breaks the bond. So what you get is you have this first, a protonated ether first, and then with water as a base, deprotonate, has a proton transfer, remove the proton. So finally, we get a sort of alcohol, but the difference is it has the alkoxide substitute in the structure. So it is both an ether and an alcohol. And so that's how we use the reaction. Depends on the solvent. If the solvent is water, you have the diol as product. If the solvent is alcohol, you get a sort of a mix between alcohol and ether. This product, by the way, is a diol. In the structure similar to the ethanol. Difference is it has one more hydroxy group. And so this compound is the, we call it ethylene glycol, ethylene glycol. Ethylene because there's CH2. There's two CH2 molecules. There's two CH2 functional groups with OH on both ends. This alcohol is very similar to the glycerol. Glycerol, by the way, is a sort of natural because most fat, animal fat, vegetable oil, they are the esters of the glycerol with fatty acid. So this is a glycerol. And this ethylene glycol, which is this, is similar. So glycerol tastes sweet, by the way. Glycerol tastes sweet. It's fairly harmless because it's not sort of natural organic molecule. It's part of the fatty acid, the part of the fat. And anyway, so the ethylene glycol, which is used in the antifreeze, have very similar taste. Tastes sweet, except this is highly toxic. This alcohol is highly toxic. Okay, highly toxic. And the reason why we use that for ingredient in the antifreeze because it can form a lot of hydrogen bond. So this compound has very high boiling point and mixed with water very, very extremely well. So basically retain the water, make the coolant antifreeze can stay the liquid as much better than without. So it uses antifreeze. And also this compound mixed so well with water, it can become very concentrated. That makes it has a very low freezing point, the freezing point depression. So that's the, we cannot really tell the difference between these two. But when you have this we find in the something strange with the acidic ring opening of the epoxide. The first epoxide, you have this one's primary carbon, and this carbon is secondary because there's a one hydrogen here. And when the reaction happens in the acidic conditions, first step, it's the proton will go on the oxygen, make it protonated, and then the halide will attack. When the halide attack, what we find from the experiment, it is a halide attack on this as a major. Gives a major product. So this reaction is more like a SN2 reaction. The reaction takes place on the less sterically hindered site. Okay, so you have this product. This is basically the SN2 product. Well, if you look at a different, also asymmetrical epoxide, where there's one carbon is primary, the other carbon, this carbon, is tertiary. Okay, what is interesting is if this reaction goes through the SN1, the halide should go here. But what we find from the experiment, the halide is actually add on the tertiary carbon. So the explanation for this, okay, the rationale for this to happen, it must be somehow when you have this intermediate after protonation become positive charge, this positive charge sort of distributed between the carbon as well. And because this carbon is tertiary, it can stabilize the charge better. So the charge basically mainly on this carbon instead of here. So that caused the nucleophile attack on the tertiary carbon. Gives this is a major product. So this is SN, basically SN1 style product. And so that's basically the SN1, SN2. You can see this theory seems like complicated, not very capable of explaining very clear. what actually happens. And so I just kind of shows you what it is, and there won't be much in the quiz or test. Okay, and then tertiary carbon is like SM1, and here is what it's. Okay, this is the reaction. Is the acidic catalyzed ring opening of epoxide in the alcohol as a solvent. So remember, alcohol again is a solvent and also a nucleophile. Okay, and this is the experiment results. Okay, we have this epoxide, and your first step just become protonated, and that makes it a better leaving group. And then followed by the nucleophilic attack from the alcohol. The nucleophilic attack, it should attack either this or this. But what do you find from the experiment? It is we have only the tertiary carbon form bond with the nucleophile. So this did not happen. Only this way happens, and for the similar reason, because this carbon, it stabilizes the positive charge better. So make it a more positive charge and make it more attracting, more inviting for the nucleophile to form bond. Okay, so the stereochemistry. This is getting interesting. You can see the methyl group was a dash, but because the reaction takes place from the other side, the end result is the methyl group becomes a wedge. So it's the inversion. It is inversion. By the way, this reaction is not 100% SN1, because if 100% SN1, there should be racemic product. The nucleophile should attack on the carbon from both directions, but we don't see that. So these are stabilized carbocations in ring opening. The 3 atom in the ring with a positive charge, it looks familiar because when we do the bromination of the alkene, we saw that the bromine cation form bond with double bond, and the bromonium, bromonium cation, okay, that have 3-member ring, and the attack come from the backside to open up the ring, and the alkene goes through the mercuration, oxymercuration, demercuration to form alcohol. That reaction also is mercury form the intermediate with the alkene, and then followed by the nucleophile, typically water attack, or alcohol, which will give you ether. Okay, so that will give you the ring open and give you the final product. The epoxide is very similar because 3 atoms in the ring, and the oxygen has positive charge. And that's basically the, it is because this carbon, because hyperconjugation from the alkyl group, is a better stabilized positive charge. So that's why the attack oftentimes happens here. It gives the major product. And in those reactions, by the way, the oxymercuration reaction gives a Markovnikov. Remember, this gives you a Markovnikov. Markovnikov product, which means the nucleophile attack on the carbon with more substituent, because that carbon has a better stabilized cation, positive charge. So here's basically the same. between this carbon and this carbon. Whichever more carbon substituent better stabilize the positive charge carbon cation, more likely to have the reaction with the nucleophile. So the epoxide stereochemistry, it depends on the condition. If the just strong nucleophile in the basic conditions, you got SN2, less sterically hindered react. With acid, it's different. Okay, with acid is different. So keep that in mind. So what this is used for? Epoxide can go through those reactions. It's pretty much summarize all the reaction epoxide can have. It's mainly subject to the nucleophilic attack and the ring opened. And so that can be used for synthesis by adding more compounds. So for example, from the epoxide attack by the nucleophile, it'll give us a substituted alcohol. And so that's basically how we would do that using the synthesis. So that's how that reaction takes place. Well, this is a little practice. We're going to have to use more reactions and use the epoxide. Because look at the final product. We start from alkene. And the final product, you have alcohol. And this is the cyanide. Cyano group. It should come from the cyanide ion as nucleophile. When you have a cyanide and nucleophile to attack on the epoxide, then we will get the product. So the synthesis, how we develop synthesis for this transformation from alkene to a beta substituted alcohol. And since we just learned about reactions, we can do the reverse. This reaction, it must come from the nucleophilic attack by the cyanide on this epoxide. From this epoxide. And there's a methyl group still here. So we do the reverse thinking. Last step, we give this beta substituted alcohol. We should form this first. And to form this, and look at our starting material, the reactant. From that, a carbon-carbon double bond, and we notice there's nothing else changed except double bond becomes the epoxide. So we can do the one step. And one step from the alkene becomes the epoxide. And there are two ways, by the way. There are two ways to do that. One is go through the peroxy acids, MCPBA. This over time we need to remember. The MCPBA is a very important reaction to give you epoxide, which is useful for synthesis. The other way, two steps. Step one is bromine and water, give you halohydrin. Second step, we add hydroxide to catalyze the ring closing, forming the epoxide. So there are two ways to give you from alkene give you epoxide, and from the epoxide it becomes a alcohol can be just one step. We add a sodium cyanide ion, where the cyanide ion is good nucleophile. Cyanide ion will attack on the carbon, and with water, finally will give us the alcohol. So this little question, the transformation, picking the reagents, is very close to the synthesis process. We develop synthesis. There's more, but I think I would just stop at the epoxide with green iron reagents, because this is the most important application of epoxide. Because epoxide have at least 2 carbons. And if the epoxide attacked by the green iron reagents, a carbonyl, will add at least 2 more carbons to the structure. And the organic synthesis is all about start from small molecules to build big molecules. There's some research group that are doing chemical research. They even start from the simple organic molecules, eventually synthesize a part of protein, or manufacture a virus, because they can put all these atoms together, those amino acids together, give you DNA and protein molecules. They can actually make that happen. Start from small molecules, eventually build a very, very big, hundreds, thousands of atoms in one molecule using synthesis. So the epoxide reaction with the green iron reagents is typically started with forming the green iron reagents. And the green iron reagents start from the alkyl bromide. And typically the primary bromide. The bromide reaction, we have magnesium and ether. This will give us the green iron reagent. Through this process, give us green iron reagent, where the R is basically carbonyl, a negative charge anion, and is nucleophile. Okay, and so the first step getting that, next step, we add the epoxide into the system, and that is the alkyl anion will attack this, open the ring, and we'll get followed by the protonation by water. We'll get a alcohol. So you can see the start from a halide reaction with the simplest epoxide. We're able to add two more carbons to the structure. 2 more carbons to the structure. So that's one way to add using the epoxide. The other way is we already made the green iron reagents in the ether. We need some polar solvent, which is ether, in this reaction. And so basically this is the nucleophile and attack on the epoxide, open the ring, give you alcohol. So in the synthesis, sometimes we write both. It depends on start from bromide. If you start from bromide, then you start from here. If the green iron reagents already pre-made, you just start from epoxide, adding green iron reagents. So that'll give you the bigger organic molecules with 2 more carbons, at least 2 more carbons. If the epoxide has more than 2 carbon, then we can add more carbons to the structure. When we add more carbons, let's see, this is the epoxide can be used to do that. Can do the product is alcohol, and with at least 2 more carbons. So this is compare. Last chapter we went over how to make an alcohol using green iron reagents. They use alcohol, forming alcohol in their product. It is basically the a halide become green iron reagents. Always same condition, use a green iron reagent. And that green iron reagents with the R as a carbonyl. This R will tack on here, and this double bond break give me the alcohol. So this reaction will give you a secondary alcohol. Okay, the epoxide reaction with the green iron reagents give us a primary alcohol, so it's very nice. Give us primary alcohol. They are different. So here's the example. You combine more reactions. How to get a certain product. Okay, so let's see. We have this, a alkene, and finally it becomes the double bond is gone. We add the OH, OMe, and form the hydroxy group. The last step, this reaction, okay, we're thinking reverse. To get this, the better way it is use start from the epoxide. And the epoxide, if attacked by the alcohol, will give me this product, because the alcohol oxygen open that can attack the carbon and open the ring, give me that. So basically, the last step, it should be the epoxide with alcohol reaction. But we need to get this epoxide. Okay, we need to get this epoxide. To get this epoxide, of course, we start from alkene, just like we learned before. So we should have a start. We should have a. Oh, sorry. There's a methyl group I forgot, left it out. I should keep that. That should not be lost. From this epoxide, we should have this alkene. Developing synthesis is about running backward. Okay, so we should have this and use the MCPBA to form epoxide. Well, to get this, and now you look at this, my starting material is alkene, and I want this alkene. They are not the same. So that means I have to use some reactions, find them, kind of move the alkene to where I want it. Okay, I need to move the alkene to where I want it. Move the alkene, it is based on the reactions of alkene, because the alkene, and the most often way to move the double bond, it is through the hydrohalogenation, adding the HBr, hydrogen bromide, and then use certain the specifically tailored strong base. It goes through elimination to get a desired product. So we need to move the double bond from outside the ring to inside the ring, to move here. Okay, the one here. And so now I have to think about what kind of ways, because there are two ways to add the HBr. One is just the normal HBr, the carbocation mechanism. The other way, it is peroxide, free radical, anti-Markovnikov. Which one? Well, since this alkene is asymmetrical, and HBr only, no hydrogen no peroxide, should give us Markovnikov. Okay, so that should give me this is the product. And the other way is use hydrogen bromide with peroxide. That will give me anti-Markovnikov. Okay, Markovnikov is bromide add on the carbon with more substitute here. Anti-Markovnikov is bromide add on this carbon. Okay, so which one of these two can use elimination, give me this as a product? This or this? Okay, this one, if it goes through elimination, base means that when you remove the beta hydrogen, which is here, this beta hydrogen. Remove this beta hydrogen, remove the bromide, that'll give me this alkene, which is the starting point. This is not going anywhere. Elimination of this halide will not give me the product. Okay, so it has to be this. And the elimination, as we learned, there are two kind of base. One is Zaitsev, the other Hoffman. And we can see the with this bromide, we have two kinds of beta hydrogen. We have beta hydrogen here, or here, the same thing, or beta hydrogen here. This beta hydrogen. The elimination will take place on the less hindered here if the base is very bulky, like T-bulk. So we need to try both. Let's try that with T-bulk. With T-bulk, the elimination happens because this carbon and methyl group have 3 hydrogens, whereas those beta hydrogens have an alkyl group around. So T-bulk should eliminate the hydrogen with less steric hindrance, which is this, or the less substituted. Okay, so T-bulk will give me, that'll give me back to the original product. No, we don't do that. So we use the other base. Okay, the other base, it is the S-oxide. The most common with S-oxide. And with such smaller base, reaction takes place on the carbon that has more substituted. So elimination will take place here to remove this hydrogen, or this, the same thing. Bromide eliminate and lose this hydrogen. So that is how we approach a synthesis question. Use a reverse, start from the very end, know what to do in the very end. Then we'll know what do we need, and then look for the reaction tools that we have to achieve our goal. So that's our final conclusion. First step, it must be this. Give me the alkyl halide. And second step, we pick a base. Here we basically pick the Zaitsev elimination. Give me this. And then from here, I can link to give us to form the epoxide that I want, which is the same here. This is the same. This alkene goes through the epoxidation, form the epoxide, or gives epoxide. And last step, use the alcohol, open the ring under the acidic conditions, because this has to be under acidic conditions, to make sure the reaction is more like SN1 like. And so that's basically the plan. It takes some time to develop the strategy. First step, just HBr. Second, we're going to use a strong base, but very small. Sodium S-oxide in ethanol. This is just solvent. So step 2 gives us the alkene. And then, since we need to form the epoxide, we add the MCPBA to form the epoxide. And then finally, use from the epoxide, we add alcohol as a nucleophile, and the condition is acidic. The alcohol is not any alcohol. You can see this is a methoxide ion, methoxyl group. So we use methanol. Methanol, there are many ways to write a methanol. It can be this, or you show the carbon hydrogen. Yeah, so these are fine. These are just different ways to write a methanol. So that's how the synthesis involved the epoxide. So the last part of the chapter, we just quickly go through some of the thiol, the sulfur compound, because sulfur is same family as oxygen, so they form similar compound, just like ether. So first of all, the thiols. Thiols are basically similar to alcohol. The oxygen replaced by sulfur, and naming is very similar. Naming is basically replace the OL, which is the alcohol, oxygen alcohol, by the thiol. So that's the only difference. And we actually use the full name of the alkane. Name the alkane first, and then we add the thiol. Basically, treat the thiol as a group on the position 1. The thiol compound also we call it mercaptan, mercaptans. And so the this group, ACH group, we also call it mercapto group. Mercapto is come from one of the Asian language, means sulfur. And so this compound, you can see that you have two functional groups. You have a SH and OH. OHs have high priority. So this compound parent should be an alcohol, and on the certain position have the mercapto group. This compound used to treat mercury poisoning. That's because the sulfur compound with the anion charge combined form very, very stable mercury sulfur compound. They're so stable they don't dissolve in water at all. And so if your body has a mercury ions floating around, we just add those thiol to your body and they will combine the mercury. So the mercury will not be able to combine with the protein. The point is that the toxicity of protein or heavy metal in general, it is their capability to form bond with the protein. That will disable the protein and cause disease in our body. Okay, so there's some more stuff. There's the fun stuff. The skunk use a thiol compound as the skunk spray. This is the you can see this compound, which is yin and thiol. It is about half, almost half of the skunk molecules come from this compound. It's thiol. And the sulfur skunk molecule, they are very stinky. I tell you one story. A couple of years ago, we went to Santa Barbara and then we drove on the street, and I saw from far away there's a dead body on the street, and it looks getting closer. It looks more and more like a skunk, and the dead body with all the intestines all sprayed on the street, and I still try to basically not get too close. But even I drove very far away from the dead body. Later, my car starts smelling because the tire pick up some juice, pick some body fluid, and then the car smells for like a half an hour as I keep driving. So they're very powerful. It's a very poor skunk. Yeah, when I was in UCR, I saw the skunk all the time. They parade in the UCR campus by the family housing. It's quite a scene. Okay, the methane thiol, this is the smallest sulfur compound. We use that as, it smells so bad and it's so strong. We just add about a part per billion concentration into the natural gas and give it a smell so that people can detect the gas leak. Not because it smells good, because they kind of warn people. They're so obvious, the sulfur smell, and they're very unique. We don't add perfume to natural gas because they're too expensive. We add something very, very smelly and very, very tiny amount is enough to give us a warning. Okay, sensitive thiols, they are used the SN2 reaction from the halides SN2 reaction. So remember, this sulfur compound is a very strong nucleophile. They are stronger than oxide, than the hydroxide or alkoxide ion, as they're even stronger nucleophile. So the reaction takes place very quickly and goes through SN2. By the way, this is secondary carbon. It should be both SN2 and SN1. But since this is such a strong nucleophile, it'll go through SN2 guaranteed. It will not wait until the carbocation form then react. All right, so those reactions SN2, we're supposed to have the inversion taking place. And so with the primary, there's no difference. It's just the SH together as a nucleophile, so it forms the thiol. This is going to be a very stinky compound, just like we add to the natural gas. And with the chiral center, if the alkyl halide with chiral center, and this is secondary, so there should be the inversion taking place. Same as mercaptol as a group, substitute group. Thiol compound, they are more acidic than the alcohol. Alcohol and water pK, it should be around 14 to 16. That's for the alcohol. And you can see the thiol is more acidic, tens of 1,000 times more acidic, and mainly because for the same reason. If you remember the halogens, hydrochloric acid much more stronger than the hydrofluoric acid, and same as here. The ACH is much more acidic than OH. It is because the atomic radius difference, and the bond is the weaker in the SH. So therefore, easy to break and the stronger, more acidic. And so that's the acidity. If you are to predict what will happen between these two, is this reaction? This reaction should be reversible. But which way is more leaning towards? That depends on which one is more acidic. So go back to the chapter 3. We introduced the rule how we predict the acid-base proton transfer reactions more leaning toward the reactant or product. It depends on the acid, which one is stronger. If the reactant acid is stronger than the product acid, between these two, this is the acid because this compound, sulfur with single H, later becomes sulfur only. So this molecule lose the sulfur, lose the hydrogen, which make it an acid. This is acid. Of course, this will be the base. And look at the product, water will be the acid for the same reason. Okay, is this reaction leading towards a reactant or product? We compare the pKa of these two. Low pK gives a strong acid. ACH, pK is 10, about 10.5 pK. Water pK is almost 16. So you can see the acid as a reactant is stronger than the acid as products. So therefore, this equilibrium must leaning toward the product. And so that means a thiol compound can be deprotonated by hydroxide from the hydroxide ion. So this is actually bring up a very interesting point. I just realized the let's say for some reason the house smells like a sulfur compound. It really stinks, and it's probably come from thiol, the alcohol. And one way to eliminate the thiol smell, it is we spray the sodium hydroxide solution. The sodium hydroxide will react with the thiol becomes an anion. The anion will be soluble in water. And so by forming thiolate ion, the thiol, the alcohol, sulfur alcohol will be removed from the air. So that'll make it reduce the smell. And so if some of you remember, I mentioned about the how to remove the acid smell is by adding base. And yeah, this is one way to do that. There's a yeah, thiolate is even better. They're even better nucleophiles compared with the thiol because they are more negative charge. Those are great nucleophiles. The thiols in real life have a very unique reaction because sulfur compound has a lower electron activity. So sulfur easy to lose electrons. If the sulfur compound lose electrons, they can form bonds. So here's the thiol compounds, they can form disulfide. And the disulfide reaction goes through a SN2 reaction. You first form this intermediate and attacked by another thiolate, finally give you the disulfide. This reaction also, by the way, is an oxidation redox reaction. Even though it's SN2, it's actually an oxidation reaction. Oxidation of sulfur. Because bromine, you start from element, and all the bromine become bromide. Bromide ion. And the electron come from sulfur, so sulfur being oxidized. That's how the disulfide bond can be reduced, again, just reverse by adding hydrogen somehow, adding hydrogen. And we can actually use this reaction. The ladies or men, they do the perm, the hair styling. If you want to make a curl to the hair or de-curl, remove the curl, we can use this reaction. The hair is basically has all the protein fibers, and the hair have a certain texture, either curly or straight, because it has a lot to do with the sulfur bond. One of the amino acid has sulfur, and so those amino acids become protein in the hair. They can cross-link from the disulfide bond, and which will maintain the certain hair style. Is it straight or curved? And so if you go to the store, do the redo the hairstyle, redo the styling, we add there's some reagent chemicals to react with the hair. It's basically is a reducing agent, will react with the disulfide bond in the hair to break up, become thiol. And then we use the styling tools to make a curl or whatever style. And then we add the oxidizing agent. Okay, we use typically hydrogen peroxide. That'll be the most common, and it's very safe and they're clean. Use a hydrogen peroxide and mix with some other reagents. Treat the hair again. And now the hair has been bent or twisted in a way. And when the reaction, this reaction will basically will form the new disulfide bond. After the new disulfide bond is formed, your hair will have a new texture, or either from curly become straight, or from straight become curly. So that's how we use the disulfide, the oxidation or reduction, to do the hair styling. The sulfur can also form like an ether. They also stinks, just like the thiol, maybe to a lesser degree. Just they are very similar to ether, so they can form similar bond. We call diethyl sulfide. It's a sulfide because this sulfur, both ends link with carbon, almost as if a sulfide ion react react with two, combined with two metal cations. And the reaction, forming the reaction, use the from alkyl halides, use the alkyl halides, and use the thiolate as a nucleophile. Again, this thiolate is very, very good. It's probably the best nucleophile, and the reaction very easy, SN2 reaction. And the sulfide reaction, it has some reactions, but in the future we won't be really dealing with the sulfur compound. Just a very unique is the ether, as you remember, is it has long pair electrons. This should be a nucleophile, but ether almost never have any real reactions as act like a nucleophile. Sulfide, the sulfide, like a sulfur ether, it does. The lone pair is loose enough from the sulfur. It can still react with, go through the nucleophilic substitution reaction, SN2 reaction. And the SN2 reaction, sulfur use lone pair to form bond. Sulfur ends up as positive charge. And this positive charge we call sulfonium, for sulfonium ion. It's very similar to bromonium ion. And this reaction is an intermediate, because once you form, notice this part almost like a ether. If you consider the replace sulfur with oxygen, almost ether, which is good leaving group. So that means if the next a stronger nucleophile to come back to attack, the nucleophile will take the methyl group and release the sulfide. So basically, sulfide here used as a tool to do the methylation, reaction. Anyway, there can be oxidized because sulfur and form the sulfoxide, all the way to sulfone. We don't need to worry about those naming, just different compound as we learned before. Okay, sulfide reducing agent, because sulfur have a low electron activity, can give away those electrons and form the DMSO. DMSO, by the way, is a protein solvent we use in the SN2 reaction, just like the DMF, acetone. So those are the polar A protein solvent. Okay, so that'll be all for this chapter. We use a little bit over time for the discussion.